Hello everybody, welcome back. It's good to be with you again. Miss having you in class and seeing you in person. We're going to continue looking at trigonometric identities, and last time we looked at where some of these identities come from and what they are, and you see here on the screen these are the 8 trigonometric identities that I had you write down and make flashcards for, and I hope that you are using those flashcards and memorizing these statements. Primarily, the way we use each of these statements is for substitutions in order to simplify expressions or change expressions to make them more useful. And so what we'll be doing today is some examples of how we can use these to simplify expressions. Eventually, this will be helpful as we learn how to solve trigonometric equations. Okay, here's example number 1. We have an expression, secant theta, cotangent theta, sine theta. And the directions say to start by writing the expression in terms of sine and cosine, and then after that to simplify so that no quotients appear in the final expression. Okay, so anything that's already in terms of sine or cosine can stay as it is, and anything that's not needs to be changed. So secant theta, remember that's equivalent to 1 divided by cosine theta. So we replace secant theta with 1 over cosine theta. Cotangent theta, remember that is equal to, well, we have a couple of options. We have cotangent theta equals 1 over tangent theta, and we have cotangent theta equals cosine theta over sine theta. We're trying to get this in terms of sine and cosine, so let's go with the second option. So we're going to replace cotangent theta with cosine theta over sine theta. And then sine theta is already in terms of sine and cosine, so it stays as it is. Okay, let's look at what we have. Notice that you have a cosine theta on the bottom and the top. You can cancel those. And notice that you have a sine theta on the bottom and the top. You can cancel those. So that means all we have is 1. So this expression that we were originally given is a special form of 1. It's just equivalent to 1. Okay, let's look at the next example. Number 2. So if you were doing this problem using your textbook, they would give you the exact same set of instructions. It would say, write the expression in terms of sine and cosine, and then it would say, simplify so that no quotients appear in the final expression. But I'm going to tell you that I don't always follow that advice. I'm a bit rebellious when it comes to these problems, I will confess, and sometimes I find it helpful to not do the first step or to wait on the first step, and maybe if I need it later, I will use it. Because sometimes what you're given actually could be nicely replaced with some kind of substitution before you change to sine and cosine. And that often happens when you have squared expressions like this, because often you can use one of your trigonometric identities and simplify it right away. So let's take a look at the trigonometric identity that says 1 plus cotangent squared theta equals cosecant squared theta. Now, if you're not memorizing these, then you're not going to have them ready to use. You're not going to identify, like when you just look at a problem, you want to be able to identify, oh, hey, I recognize that. That looks like this. I could replace it. And if you don't memorize the identities, then you won't recognize those things. So let's start with this one, and notice what happens if we subtract 1 from both sides. We get cotangent squared theta equals cosecant squared theta minus 1. That's just rearranging that identity. So what we can do in our problem is we can replace the cosecant squared theta minus 1 with cotangent squared theta. So we now have sine squared theta times cotangent squared theta. Now that we have that, maybe there's more we can do to simplify it even further. So now is a good time to change the cotangent squared theta into sine and cosine. So cotangent theta is cotangent theta is cosine theta over sine theta. If you square that, then cotangent squared theta, let's make that a little bit better, is cosine squared theta over sine squared theta. So we can replace the cotangent squared theta in our expression with cosine squared theta over sine squared theta. Now look, we have a sine squared theta on the top and the bottom that we can cancel, and all we have left is cosine squared theta. And notice that is not a quotient, so that's about as far as we can go, and there's our simplified expression. Okay, let's take a look at number 3. We're given the same directions, but I'm going to say the same thing about it, and that is maybe, maybe not use the first step. Okay, we'll just wait and see. We want to simplify so that we don't have a quotient. Again, we have an example here where each of these expressions should remind us of something from our Pythagorean identities. And so generally, doing a Pythagorean substitution first is better than the switching to sine and cosine. So let's see. 1 minus sine squared theta. That should remind us of this first Pythagorean identity, sine squared theta plus cosine squared theta equals 1. And what if we took that and we subtracted sine squared theta from both sides? We would have cosine squared theta equals 1 minus sine squared theta. So we're going to be able to replace 1 minus sine squared theta with cosine squared theta. And then, notice, you have another Pythagorean identity that has 1 plus cotangent squared theta equals cosecant squared theta. So we're going to be able to replace 1 plus cotangent squared theta with cosecant squared theta. So let's do both of those substitutions. And we have cosine squared theta over cosecant squared theta. Now this is still a quotient. It says eventually we should get rid of our quotients. So to do that, now is a good time to change things to be in terms of sine and cosine. Cosine squared theta is already in terms of sine and cosine, so it's staying put. But cosecant squared theta, we can use this reciprocal identity, and cosecant squared theta would be the same as 1 over sine squared theta. If we just square that reciprocal identity. So we have that replacing the cosecant squared theta. So now we have something divided by a fraction, and you know that dividing by a fraction is equivalent to multiplying by the reciprocal. So let's change this, make a little space. Let's change this to cosine squared theta multiplied by the reciprocal of the denominator, which means multiplied by sine squared theta over 1. Okay, so there's nothing more we're going to be able to do with this, except for we could just write it without the 1 on the bottom, and we don't really need the dot in between. So cosine squared theta times sine squared theta. That is our simplified expression. Okay. Number 4. Now sometimes it just says simplify. Sometimes there's no guidance. What we can do is rely on our previous knowledge of what we did in previous problems to simplify, like maybe we're going to change things to sines and cosines. Maybe not. We'll just see what happens. At this point, we have something that we can distribute, and so we're going to multiply tangent x and cotangent x, and then we'll multiply tangent x and cosecant x. So we have tangent x times cotangent x plus tangent x times cosecant x. Now surely there's something we can do with that. Okay, do you realize that because tangent and cotangent are reciprocals, that when you multiply them, you get 1? Every time you multiply reciprocals, you get 1. So you could take that identity that I just drew the arrow toward, and you could multiply both sides of it by tangent theta, and you would have tangent theta, cotangent theta equals 1. So we can replace that whole expression with a 1. How about the other one? For the other one, let's go ahead and change to sines and cosines. Even though the problem doesn't say we have to, now we know that that is a strategy that can be helpful. So we know that tangent x is going to be sine x over cosine x. You know it doesn't matter if you use x or theta or whatever letter, all the same concepts apply. And we know that cosecant x is 1 over sine x. Notice that we have a sine x that we can cancel from the top and the bottom. So at this point we have 1 plus 1 over cosine x. Now, in previous problems it said don't leave a quotient, so I wonder if this would look simpler if we didn't have a quotient. So 1 over cosine x is equivalent to secant x. Secant is the reciprocal of cosine. So we have 1 plus secant x. And I'd say that looks simplified. Now I will mention that the way I'm doing these problems is not necessarily the only way. In fact, when I was doing problem number 2, my plan was to show you 2 different ways to do it, and I kind of forgot. But I just want to mention that sometimes you'll do one thing and you'll end up, maybe you'll end up with an answer that seems to be a shorter route than mine. That's okay. There's often many possibilities. Okay, number 5, last example. This one also just says simplify. Well, we have a quantity squared. How about if we go ahead and square it and see what happens? Keep in mind that when you square a difference or square a sum, you have to do the FOIL process. So we have sine of alpha, another Greek letter here, sine of alpha minus cosine alpha times sine of alpha minus cosine of alpha. This is what squaring it means, right? Okay, now let's FOIL. So we multiply the first. Sine alpha is sine squared alpha. We multiply the outsides. We get minus sine alpha cosine alpha. We multiply the insides. We get minus sine alpha cosine alpha. You can call it cosine alpha sine alpha. It doesn't matter. And then we multiply the last and we get plus cosine squared alpha. Okay, now what can we do with that? Notice that we have a sine squared alpha plus a cosine squared alpha. They might not be together, but we could rearrange and get them together. And notice the Pythagorean identity, sine squared theta plus cosine squared theta equals 1. So from both of those, we just get a 1. And then the other 2 terms are like terms. There are 2 of them, so let's just combine it into minus 2 times sine alpha cosine alpha. Is there any more we can do? Well, I suppose if we had things that were not already sines and cosines, we could change them to sines and cosines to see if anything else happened. But we do already have sines and cosines, so that's about as far as we can go with that. Okay, I hope you can see how knowing these 8 identities allows you to do some substitutions and in various ways allows you to change expressions to look different or to simplify expressions. For your homework, I've put together some problems. I think there are 6 of them. They model, or they mirror, I should say. They mirror the problems that I just modeled. And so work your way through them. Check your answers. The answers are provided. And I'm also providing a video of all the solutions worked out in case you need help. And you can always ask me questions. I'm enjoying my interactions with you guys over the interweb. Thanks. Bye.